What's going on, smart people? Today we're going to be finishing up the preliminary vector stuff for this series on Tensor Calculus. So in this video we're going to be going over vector transformations and representing vectors as matrices. So let's get started. In the last video we solved the physics problem two ways, where we kept it in Cartesian coordinates with just x and y, and then we rotated it to some point x prime and y prime, and we got two seemingly different answers. But because the physics shouldn't change, there should be a way to express that those are equivalent answers. So what we're going to do is we're going to find a way to convert x and y into x prime, y prime by rotating our axis. And we're going to be rotating our axis about the z-axis. So I'm going to write the solution that we're looking for, which is x prime is equal to x cosine theta plus y sine theta, and y prime is equal to minus x sine theta plus y cosine theta, and z prime equals z, because we're rotating about the z-axis, so nothing's changing there. So go ahead and for yourself see if you can derive this, and then I'm about to go through it for you also. I'm also going to use this video to see how much you want me to go through the motions of deriving certain equations, because I do understand that this makes the videos quite a bit longer, but I still think it's worth seeing the derivation. But anyways, I'm going to get started with deriving this. So we're rotating from some point on the xy plane up to some point theta. We're down to some point theta. So normally in polar coordinates what we would say is x is equal to r cosine theta. If we're rotating from the x-axis up to some point, that's r cosine theta. And y is equal to r sine theta. And just to make sure that I end up with thetas at the end, because we're going to use two different angles, I'm actually going to start with an alpha. Cosine alpha. Okay. So this corresponds to just rotating from the x-axis up to some point x and some point y. But what if we want to go from not just that point alpha up to some point theta? So something like, here's our alpha, and here's our theta. Hopefully you can see that. Well then, x prime is just going to be this new angle of alpha plus theta. Okay, so we got r cosine alpha plus theta, and y prime is equal to r sine. Oops. Cool. Now we can just use some trig identities. The cosine of the sum of angles is just going to equal r. I'm going to distribute this r. It's going to be r cosine alpha cosine theta minus r sine alpha sine theta. And y prime is going to equal r sine alpha cosine theta plus r sine theta cosine alpha. And one thing to take notice of here is that this r cosine alpha, this r sine alpha, well, that's just our definition of x and y. So we can substitute that into this equation, and we get that x is equal to r cosine alpha, which is x, this is x prime, x cosine theta, minus y, and I'll get to why this is a minus in this derivation in just a second, minus y sine theta, and y prime is equal to, we got r sine theta, so we got a y cosine theta. Do I want to do that? That's fine. Okay, so we got that plus x sine theta. Just writing this in a similar form, that's just equal to y, oops, cosine theta, oops, Good Lord. Sine theta. Okay. First thing to notice is that we have minus sign here. This has a plus sign here. This has a plus sign here. That has a minus sign here. Minus plus sign here, minus sign here. All this is a factor of is the fact that we were adding some angle theta to this, which means that we're rotating about, we're doing a bit of a counterclockwise rotation. So if we swap theta for minus theta, meaning we're rotating clockwise, then all of these thetas become minus thetas. Okay, and cosine of minus theta, cosine is an even function, so that doesn't change. F of x is equal to minus f of minus x. Sine is an odd function, which means that f of minus x, so f of minus x is equal to minus f of x. So if we change f of x for sine of theta, then this cancels out, which tells us that if theta equals minus theta, or goes to minus theta, x prime is equal to x cosine theta plus y sine theta. And the same concept here, this becomes minus because it's sine of minus theta. And then the cosine doesn't change. Great, so this is what we have as our transformation into the x prime, y prime reference frame. Now in the first video, we defined a tensor sort of as something that obeys this transformation rule. We see all of these partial derivatives popping up. So what I want to do is I want to start showing that we can express vectors in a similar fashion. Now we just derived some transformation under rotation, so we're going to be using this effectively as the thing that we're going to be expressing transformations in and out of. What I want to do now though is I want to start taking derivatives of this. I want to see if the interval between 2 points under this rotation is invariant. Effectively, when we do these kinds of transformations, what we're doing is we're making a statement on the relativity of these transformations. And relativity is basically considered or concerned with what doesn't change under these transformations, what's invariant. So taking derivatives of this, we get dx prime is equal to dx cos theta plus dy sine theta y prime dz prime dz. Okay, cool. So what I want to see, what I want to determine is if this is true. Does delta s prime squared equal delta s squared, where delta s prime is just the sum of the squares of these quantities here. So let's see. So we have let's go ahead and write it out. So this is going to be equal to dx prime squared plus dy prime squared plus dz prime squared. And now we're going to substitute in these quantities and see if we just get dx squared plus dy squared plus dz squared. When we do that, we get this is equal to okay. And then here, we'll just FOIL this out. So that's going to equal dx squared cosine squared theta plus 2 dx dy cos theta sine theta plus dy squared sine theta sine squared theta and this is plus. So we got this times this, so that's going to be plus dx squared sine squared theta minus 2 dx dy cos theta sine theta plus dy squared cos theta squared, okay, plus dz squared. This should be a regular dz. Okay, right off the bat, these things cancel. We got 2, a minus 2. Okay. So we got a dx squared. Let's factor out a cosine squared theta. So we got, if we factor out a cosine squared theta, we can factor that out from here, and we get dx squared plus dy squared. And then we can factor out a sine squared theta, and then we get the same thing. We get a dx squared plus dy squared plus this dz squared. Okay. Cosine squared plus sine squared is 1, which tells us that this is equal to dx squared plus dy squared plus dz squared. So what we showed is that the space-time interval, if you're not familiar with that terminology, don't worry about it, but the space-time interval is invariant under this transformation. So this interval is invariant under this type of orthogonal transformation, which is pretty important. Now that we showed that, what we can do is we can take another invariant quantity in classical physics. We can take the concept of time and multiply these equations by 1 over dt. And when we do that, this whole thing becomes Vx prime equal to Vx cosine theta plus Vy sine theta, and a similar process for those ones. And we can do this again. We can do this equation by dt, and we can get an expression for the acceleration in the x prime direction. This should be prime x, I guess. And what we see here is we have a transformation of something that looks like vectors more. This still technically is, but this I think visually looks like one more. Plus ay sine theta. But what we see is that the components of ax prime and ax aren't necessarily going to be the same thing. They will be if theta is 0, but that's because it's the same reference frame. But what happens is that the total will be the same. The same physics should apply, which means that F equals ma and F, let's say prime, equals ma prime. These both have the same relationship. The physics is still the same in two different frames of reference. And I think now we're ready to start connecting the dots between things like this and things like this. So what I'm going to do is I'm going to take the derivative of x prime with respect to x. So let's say dx prime dx, that's just going to be cosine theta. And then I can say, what's dx prime dy? That's going to give me a sine of theta. Okay, and then I can also do dy prime dx and dy prime dy. And we're going to substitute this stuff in. And what we get when we do that is that x prime is equal to x times the cosine of theta. Cosine of theta is defined as dx prime dx. So this is equal to dx prime dx. Let me write x first. plus y dx prime dy, y prime is equal to, let's say, x dy prime dx plus y dy prime dy. And then that just goes to 0. All of the all of the z prime just is still z. All of these derivatives just go to 0 for that. Cool. Now let's write this in a bit of a more compact way. The way that we can do that is, remember, x1 equals x, x2 equals y, x3 equals z. So we can write this whole thing as x prime I. So if I is 1, we're talking about x prime x, or just x prime. If we're talking about 2 here, I equals 2, then we're talking about y prime. And this is going to equal a sum. Okay, and this is always going to be x plus y plus whatever, x plus y plus whatever. So this is going to be something that's iterated through. This is going to be x to the j. So summing over j. So if j equals 1, we got x plus j equals 2, which is y. Times this derivative, and how we can express that, well, x prime is still the same. So that's going to be dx prime I with respect to j, dxj. This is a bit of an abstract way of expressing this, but I hope it makes sense. So just to go through it once, if we want to do 1, x prime 1, well, that's just equal to x prime. And we're summing over j, so it's going to be x1, which is going to be x times the derivative of x prime 1, because that's what we're working with, dx, because x or j is 1 for right here, plus, remember this is a sum, j equals 2, which is y, dx prime dy. So we get that back. So this is talking about specific components. Okay? But we're not, so now, when we realize that we can describe any vector that is sort of derivative of this displacement vector, remember we just multiplied by 1 over dt to get a velocity, and we could get acceleration. We could scale it by some mass to get a momentum. Anything that comes from this is going to obey this kind of transformation rule. So what that tells us is that we can construct an arbitrary vector, A, some vector A, where A, let's say, prime x is equal to ax cosine theta plus ay sine theta dot 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 dot. Which tells us that any vector here can be expressed a prime I is equal to the sum of a, or summing over j dx prime I dx j. Okay, and it's still dx here, it's not dA dx, because we still define this cosine theta in terms of the derivative of the displacement parts, or of the displacement transformation. Okay, so this is now defining a vector by how its quantities transform. This is very, very similar to how we define tensors. What I'm going to do now is we're going to start switching up our way of representing vectors. We're going to learn how to represent them in terms of matrices. And if you've had any quantum mechanics, this part might not be too different, or might not be too new for you. So what we're going to say is, like, if you impose any kind of coordinate system on a vector, you can express that vector, say vector A, into its components, A, B, and C. But what you can also do, and this was really made popular by the physicist Paul Dirac is we're going to learn how to use Dirac's notation. Dirac's notation, okay. And what we say is that this little ket vector is represented by a column matrix of A, B, and C. And both of these contain the same type of information. The only things that change are the way that we actually carry out the calculations, but nothing else changes. So for example, we could write a vector, a force vector F is equal to some scalar mass times some acceleration vector. If you were to expand this, this is saying that you're taking, say that we're working in Cartesian coordinates, Fx, Fy, Fz is equal to some mass times Ax, Ay, Az. So that should probably have been, there we go. Cool. And we can also do things like dot products and stuff between these, but we have to express them in a little bit different of a way. In order to take the dot product of a vector that's represented as a column vector, is we first have to transpose it, assuming its components are just real. So I'm going to go through the assumption that this vector, all of its components are real. If they're not, then you have to also do the conjugate, the complex conjugate of this. So say I have a vector B also, E, F, G, well then we can take the inner product or the dot product between these vectors, A, B. Now you'll notice that this A isn't pointing in that direction anymore, it's flipped over. And what that tells us is that this column vector now becomes a row vector. So this is equal to A, B, C, E, F, G. Just realized I skipped a letter. Whatever. And now to do this, all it is just the basic rules of matrix multiplication. So that's equal to AE plus BF plus CG. And this is sometimes known as the contraction, because what we're doing is we're taking two vectors and we're contracting the components into one number. Because this is all just going to be one number at the end. It's the dot product. Now we're mostly going to be working with real components of vectors, but just to be clear, just to be thorough, say if we had some vector A, some vector A that has some complex components, I, 0, say 1, then this becomes minus I, 0, 1. So if we're dealing with ones where the components are complex, you take the complex conjugate. We're not really going to be working with this, but I just didn't want to say anything that wasn't exactly correct. But we can also form with something that's called the outer product of two vectors. So when we did the inner product, we had A, B, we had a nice little form bracket, the outer product, so this is inner product. The outer product is going to look something like this, A, B. So if we take these to be the same column vectors that we had before, column and row vectors that we had before, A, this is going to equal, A is a ket, so this is a column vector with its components A, B, and C still. And now B is a row vector, E, F, G. And what this is going to give us is this is actually going to give us a square matrix, so it's going to bring up the dimension of the new vector. So this is going to be equal to AE, AF, AG, BE, BF, BG. This is together. So that is what we call the outer product. And we can also express our very familiar unit vectors in terms of column vectors. So let's stick with Cartesian coordinates. So we have I hat equals 1, state 1, which is equal to 1, 0, 0. It's unitary in the first component, in the x component, and 0 for the others. J, state 2, 0, 1, 0, and K, 0, 0, 1. And we can also do something like determine what the inner product between these unit vectors are. So we could take, say, the inner product between I and J. But I'm not saying IJ is I hat, J hat. I'm just keeping this general. But we can solve a specific case. We could find out what the inner product between state 1 and state 2 are. And that's going to give us, well, 1 is now a row vector, 1, 0, 0, times the column vector 0, 1, 0. And that's going to give us 0 plus 0 plus 0, which is equal to 0. We could do 1 and 1. That gives us 1, 0, 0, 1, 0, 0. And that gives us 1. In other words, ij is equal to delta ij. It's 1 if they're the same, it's 0 if they're not. This is nothing new. This is just formulating the definition of dot products between orthonormal basis vectors in terms of column vectors. So the concept isn't new, but this notation might be. We can also formulate our completeness relation by saying that the outer product, let's say 1, 1 plus 2, 2 plus 3, 3. Well, we can find out what this is. Okay, so this is going to equal, so 1, 1 is going to equal ket vector 1, 0, 0, 0, oops, 1, 0, 0, which is going to give us a square matrix of 1, 0, 0, 0, 0, 0, 0, 0, 0. And if we do 2, I'm just going to do this one, and then I think it'll be clear how the next one goes. Okay, so we got 0, 0, 0, and then we got a 0, 1, 0, and a 0, 0, 0. And we can go ahead and just write out the one for 3, inner product for 3. That's going to give us 0, 0, 0, 0, 0, 0, 0, 0, 1. But when we add all of these matrices together, what we get is that this is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Sometimes just 1 with a bar on it. It's the identity matrix. And that is a statement on the completeness relationship between these unit vectors using this Dirac notation. And since we have this completeness relation, we can express any vector, say A, in terms of its, say, A1, 1 plus A2, 2. Okay? So what that tells us is that we could take, say, the inner product between I and this vector A, and that's just going to give us the ith component. Right? This is similar to saying if I take the inner product between I hat and I hat dot A vector, that just gives me AX. Right? So this is just the same statement. So what we can do now is we can start with the completeness relation. So the identity matrix is equal to the sum of some if we have some set of orthonormal basis vectors, the sum of their outer products, summed over alpha, gives us the identity matrix. That's what we just did here. So if we multiply this by some vector A, so multiply by some state A, well, A times the unit vector is, or not the unit vector, by the identity matrix is just going to be A on the left-hand side. So we have A is equal to the sum of, let's say, alpha A. But we already know what this is. This is just going to give us the alpha component of this. So that's going to give us the sum over alpha of A alpha. There we go. So this is essentially effectively what we just set up here as well. So now let's say that we have some matrix M, some square matrix M that's defined as the outer product between two normal vectors, A and B. And I want to mathematically define how to pick out a specific element in this matrix. So what I want to say is I want to find the mijth component of this matrix. Okay, well, let's take a look at this. Say I want to find M1, 2, where I'm saying I want the first row and the second column element of this matrix. Well, what we can do is, let's take 1 times this matrix M and see what we get. So we're just starting with this. I'm not making any insinuations that this is going to give us a row vector or a column vector. We're just going to see what happens. So if we do this, this is equal to the row vector 1, 0, 0, because that's just the x hat basis vector, times M. And M is a square matrix, so that's just going to be some elements M11, M12, M13, M21, M22, okay. And when we multiply this together, we get M11, then this is 0, M12, then this is 0, M13, then this is 0. So this spits out another row vector. This is going to give us M11, M12, and M13. Okay? Now, what we can do is we're going to find out what this is. M1, or 1M2. So we're sandwiching in essentially this M in between the two things that we're going to assume are the row and the column. So that's going to equal, well, this we just found, that's just this row vector. So that's M11, M12, M13 times the column vector 2, which is just the y hat unit vector, 0, 1, 0. We get M11 times 0 plus M12 times 1 plus M13 times 0, which is giving us M12. Cool, so now we have exactly the matrix element we were looking for. Put more generally, Mij is equal to Imj. And this is something you use a billion times in any quantum mechanics class. But at least as far as mine went, we didn't go as far as actually building out the matrix. We just sort of used this relationship. So I think it's pretty useful to see it actually written out explicitly. Okay, and the last thing that we're going to do here is we're going to learn how to transform into a different basis using Dirac notation. So let's say we're going to start off with the normal completeness relation, which says that the identity matrix is equal to the sum over I outer product with I. So this is going to be our usual set of basis vectors. This could be like ijk or something. And we're interested in transforming it to a set of new basis vectors that also obey the completeness relation. that we'll leave in terms of alpha. Okay, so this would effectively be like your I primes and your j primes and your k primes. What I'm going to do here is, again, I'm going to multiply this entire thing by the state vector A. So that tells us that A is equal to the sum over I of I, A. And we know what this is. This is just the inner product between your basis vector and your normal vector. That's going to give you the component of that. This is effectively just I hat times A, which is going to give you the ith component of A. This shouldn't be anything too new. So that's going to be sum over I, A is equal to A. So our vector A can be written as a linear combination of all the basis vectors summed over times the ith component of that vector. So written out more explicitly, this is just the same thing. If we were to switch back to the old notation, this is the same thing as, I hat AI plus j hat AJ plus k hat AK, where this is like your x, y, z, or whatever. Okay, so this is just saying again that we can express any vector as a linear combination of unit vectors scaled to some degree. And now what we're going to do is we're going to learn how to transform into this new basis, into this alpha basis. So one thing to keep in mind is that if we want a specific component of a vector, we can take the inner product of the basis vector with that vector. So if we want to find the alphth component of A, if we want to transform into alpha, all we have to do is take the inner product between alpha and A, and that's going to give us a sum over I still of alpha I A to the I. And this is the way that we're transforming things in Dirac's notation. So this is equivalent to saying what we said before. If we were to say alpha prime or A prime alpha is equal to, the sum over, let's say, j of A to the alpha, no, that's going to be A to the j, d x prime alpha dx j. So these are equivalent. This is just expressed in a different way. But this is how we transform in Dirac notation. This is how we transform in regular. And if we sort of compare these two equations, what this tells us is that dx prime alpha dxj is the same thing as this inner product here. And we also call this lambda alpha I. Okay, so what this tells us is that we can rewrite this entire thing. We can transform from A into the A prime reference frame by this transformation here. So we have A prime is equal to lambda alpha I A. And that's pretty much going to do it here for this preliminary vector stuff. The vector review is done. I think now it makes more sense why we can express vectors in terms of how they transform, and that should make it a bit easier to grapple with the fact that that's how we define tensors as well. Speaking of, in the next video, we're going to jump right into two-index tensors. Hope you guys found this video helpful. Let me know in the comments section if anything I did here was unclear. I'd love to answer any additional questions, and I'll see you guys there.